Right then, so the next part of chapter 19, connected particles, could be called systems of particles. It's the start of all questions where it could be cars, caravans, trains, carriages, bicycles, trailers, where you've got one thing pulling another thing along, or one thing braking and braking for both of them. Connected particles, systems of particles. It starts in the book with a tip saying that the word string can be used for anything that is flexible. I've got a string here. A computer cable could be a string. A string, you can pull something with a string, so it can have a tension in it. You can't push something very effectively with a string. The word rod is going to be used for something which we can either pull something with or poke something with, okay? And I think we had that, the difference between tension and thrust earlier in the course, I'm sure, okay? So tension will be a pulling force. The compression force is here. As you push something that's rigid, if I take my Sharpie and I'm pulling the ends apart, there's a tension in it. If I'm pushing the ends together, that's a compression force. In the pen, there's a thrust. As I'm pushing with both hands into the pen's pushing outwards on my hands, okay? A rigid object can have a tension or a thrust in it, and a string, if I had a string in my hands, I could pull it, there'd be a tension in the string. If I pushed the string together, it would just collapse, okay? And the next point I wanted to make, key point 19.4, this is about the 1 mark parts to the ends of questions, what assumptions we can make. If something's described as inextensible, as in it cannot stretch, it's not elastic, that means if two things are connected by something that doesn't stretch, as one thing sets off, the other thing sets off with it, okay? When we're dealing with things over a pulley, as that thing drops, this thing rises, and with no stretch, they both accelerate together. They have the same velocities together, while the spring is taut. Now there's a good word, taut. 3 ways of spelling taut, all having different meanings. This is the one which means something's under tension, okay? If something is described as light in a system, then its mass compared to everything else is negligible. We can ignore that mass. If we're dealing with a car, which is the best part of a ton, pulling a caravan, which is a fraction of a ton, we can ignore the mass when we're doing Newton's second law of the cable if it only weighs a couple of kilograms, okay? So inextensible and light have specific meanings in these questions. I'm just going to do the 2 examples from the book and then set you loose on the questions. And next week we'll build some practice time in. So the first example, a car 3/4 of a ton pulling a trailer which is just over half a ton with a light, inextensible cable. A cable is something that can have a pulling force in it, but not a pushing force, okay? Light, we can ignore its mass. Inextensible, as the car moves, it pulls the trailer with the same acceleration. And we've got a driving force and resistances of 800 and 600. And these are the things we want to find: acceleration, tension, and the assumption parts of it. Right, my diagram would always look like this. The whole system in a big diagram showing the forces clearly. Now in this case, what are the forces? We've got a driving force which acts on the car, a resistance which acts on the car, a resistance which acts on the trailer. So that's where I've drawn the forces. And because it's a cable, we've got a force pulling the trailer forwards, which is a tension, and that force is pulling the car backwards, okay? That's important. The tension in both ends of the cable is equal and opposite. And in the same way, if we connect two things with a rod, and actually the two things are pushing in on the rod, then the thrust at each end of the rod will be equal and opposite. And that's the very next question. How would I do this? You can, and this is what I'm going to say about the pulley questions, you can draw a box around the car, and we can just consider the car. Newton's second law, to the right, that force, take that force, take that force, is mass times acceleration. We can also construct an equation of motion if we draw a box round the trailer, and then we simply have Newton's second law to the right. Notice that in this application of Newton's second law, T is positive, it's to the right. The tension, the pulling force on the trailer, take the resistance, is its mass times acceleration. Okay, notice that we've got T in both equations of motion, but equal force, but opposite signs. If we added those two equations together, we'd have 1800. The T's would cancel, and we'd have take 800, take 600 is the combined mass times the acceleration. That's what I will call Newton's second law for the system. That's effectively looking at the forces within this box where the T's cancel. Okay. If we take that third equation, that one there, we can solve that and find the acceleration. And then that acceleration we could substitute into equation 2 and get the tension. So how could we have got the acceleration straight away? We could have jumped straight to that third equation. But to get the tension, we would still have needed either of equation 1 and equation 2. So you still have to write them. So your choice is, if you're ever stuck, you can just construct the first two equations and then see what you need to do. The final part of this is the word light means that, the word inextensible means that. Learn those definitions. If it ever comes up as a 1-mark question, just write those. Second example, trailer attached to a car by a tow bar. A rigid thing, not a, I should have more properties, shouldn't I? Not a bendy thing. The RAC green flag use tow bars. Why do they use tow bars? As the towing vehicle is pulling the car along, absolutely fine. If the towing vehicle brakes and it's just the rope, an inattentive driver at the back tends to just run into the back of the towing vehicle. Separate them with a bar, it can pull them, but it always keeps them separate. What does that mean for exam questions? As soon as they mention tow bars, be wondering if you're going to be asked for the pushing force in a bar. Right, how do we know there's going to be a pushing force? The car brakes and decelerates. Okay, what does that mean for the diagram? Okay, the acceleration, here's the car. Here's the trailer. The acceleration is this way. Or it's minus 46 measured to the right of the diagram. So if it's braking, the acceleration is that way. Newton's second law for the car. Now this is the crucial bit. So the car has a braking force. The car's braking force is providing the deceleration. So the braking force, B, is in the same direction as the acceleration. The trailer, there's no mention of brakes on the trailer. The only reason the trailer is slowing down is because the force in the bar is pushing it backwards, okay? If the bar is pushing the trailer backwards, the bar is pushing the car forwards. That makes this force a thrust. Why is it a tow bar, not a cable? Because you can't transmit a braking force to the towed object with a cable. Right, so for the car, we have just those two forces acting on that mass and that acceleration. We get that equation with two unknowns in it. For the trailer, we just have one force acting with a known acceleration and a known mass. We'd get this equation, which, as you'll notice, we could solve straight away for the thrust. But just to make a point, if you added those two equations together, the thrust would cancel and would give you the braking force, if we were asked for that. But in this question, find the thrust, only that equation was needed. We can just solve it. So, if in the question you spotted you only needed equation 2, full marks. If you're in any doubt, construct both equations, then sit down and think what you're trying to find. Right, I might be setting a record here for short videos. Things I don't like in the book. I don't like the way they separate the diagrams out like that. I don't like the way they put the forces here. I don't like the fact that they're drawing pictures of cars and caravans, which is going to take up time in the exam. Okay, so I wouldn't do that. Do them like I've been doing them. Right. Mechanics, start with a big clear diagram. In this case of the system, but make sure you're clear about which elements of the system the forces are acting on. If need be, once you've drawn the system, draw separate diagrams for all the elements, like we did for the people in the lifts. People in lifts are another sort of connected particle question. Then write down the equation. If there's any acceleration, write down the equations of motion, Newton 2. If in doubt, just write every Newton 2 equation. The object in front, the object behind, the whole system. Sometimes you can shortcut it by just doing the system as a whole. If in doubt, do all of them. If it's not accelerating, balance the forces for each element of the system, or the system as a whole. And once you've either done that, if it's accelerating, or that if it's in equilibrium, you'll have 1, 2, or 3 equations which you then go on to solve if it's just one equation you need, or solve the simultaneous equations, which are only ever going to be as complicated as linear, quadratic, or very simple cubic or quartic if you can use the fact theorem. Right, 19B has 9 questions. Even ones is 4 questions. Treat yourself to question 9 if you have time. Next week, we'll do the online lessons for pulleys, which will leave us a spare lesson, and then we'll spend some time on the mixed exercise, and then we'll see if, when we're in or when we're not in, and how we'll use the rest of the time. Okay, good luck with that. Still less than 15 minutes, which is good, isn't it? Oh, my group, I'll make an Edmodo exercise, submit yesterday and today's work to the Edmodo exercise when I've done it, by the end of the week, please.